gear and gear unit design theory and practice. We are in module 2, which is design of spar, straight and helical, bevel and worm gears. And this lecture is on design of bevel gear. In this lecture, first of all, we will go through the concept and feature of bevel gears. Next, nomenclature and geometry of straight bevel gear, formative number of teeth of straight bevel gear, typical gear unit with bevel and helical gears, bending strength basis design of straight bevel gear, that is you can say Lewis formula, wear load capacity and probable dynamic load in straight bevel gear, and finally, tooth load in straight bevel gear. Now, bevel gear we need when the shafts are not only not parallel, normally they are at 90 degree, and in the simplest form axis of the pinion and axis of the gear, they are intersecting as shown in 3D view. Now, this angle so this is the axis and this axis. In this case, what we have shown this they are intersecting. This is a straight bevel we have shown, straight tooth bevel, and this angle may be 90 degree or may be different. It might be more than 90 degree or less than 90 degree also, but in common cases you will find this is 90 degree. Now, bevel gear again it might have also the shafts are not intersecting. It is 90 degree, less than 90 degree or more than 90 degree, but they are not again intersecting. So, that is possible with offsetting the inclining tooth in a directions, and those are usually not straight inclination, that is in sort of some spiral. So, with that we have different kind of bevel gear also. So, this is a spiral bevel gear is shown. In spiral bevel gear, as we see the tooth are spiral form. It is same as in case of helical gear, in case of spar gear, straight tooth spar gear or helical gear parallel shafts. Here in spiral bevel essentially the axes are intersecting. Although these are spiral, but these are intersecting as you see. But there is another, as I told, that this is offset. This offset is shown both in this left hand figure and also in this figure. This is called hypoid bevel, and this hypoid bevel are widely used, and it is having better performance and tooth load carrying capacity also, as this is an offset that gives many advantage. So, for an example, in case of differential gearing, that tail shaft is coming at a point, but the whole unit can be lifted depending on the diameter of the wheel etc., and there will be more under clearance below the differential unit. This is just to say this is one advantage, but in fact if we think the strength point of view, smooth operation, where all such point of view, hypoid bevels will be better than straight bevel and as well as than spiral bevel gear. But spiral bevel gear also very close to hypoid bevel gears. Only thing in if we need that shafts are intersecting, we have to go for spiral bevel gear. Now, this design of hypoid and spiral bevel gears are relatively complicated, and in many cases these tooth generation also complicated, and that is some special methods are used which are recommended by the manufacturer of such bevel gear cutting machines, and they also suggest how to calculate the strain and other part. So, straightway you will not find any design methods of hypoid and spiral bevel gear in machine design textbooks. Now, if we think in other way that shafts are not intersecting at all and but shafts are 90 degree. So, gradually we arrived into another type of gear which is worm gear. Worm, this is bottom one is called worm, the top one is called worm wheel. Okay. So, this is the transformations of bevel gear to worm gear, it is shown here. And also herringbone bevel gear is possible, but normally these are not used. As you find in case of herringbone, the tooth has inclination in both directions, very close to spiral bevel gear, and it is having better load distribution over the shaft. But normally these are not very expensive to generate and not normally used. Now, coming to the nomenclature of bevel gear, this is of course straight tooth bevel gear. Here we have shown the different dimension and different terminology. So, this is basically you can read, but I would like to mention few points. Now, as you see, these teeth are definitely it is a conical in shape, and for a 90 degree shaft they are meeting like this. Now, these are called cone angle, and this is the pitch angle, pitch axis it is called. This distance is called crown distance, this is face angle, and others are written here. Importantly, this point, if we consider this point to the center, this diameter is outer pitch diameter, which is defined by d o or d 0, and radius is defined by r 0 by r by 2, whereas at inside this radius is d I by 2, radius is d I by 2, and another important part which we need in design, that is the width of this teeth and this length from the cone apex or pitch apex to the back side of the gears. Now, again another important issue is here, that this is we consider a mean value of this pitch circle, which is called, which is this radius is called r m, which is r I plus r 0 by 2 or d I by d 0 by 4. Now, this is will be slightly shifted, it is at the midpoint. Okay. So, at the midpoint, this sometimes all references are given to that mean radius. We have followed in this design, in the design procedure, that radius as the reference radius, where if we cut that surface along AA and look into from the vertical directions, we will look the standard straight tooth spar profile. If we take section along AA, I repeat, and if we look from the perpendicular direction, we will see this cut section as a like this, as a straight spar gear, and this then in that case we can consider this angle is the standard pressure angle. Suppose if we take 20 degree, that is this alpha will be 20 degree, as well as if we measure here. So, this will be circular pitch from this point to this point, it will be the circular pitch, this is pi m, and also at that section the module we can consider the module is standard. That means, if the teeth number is say 50 or Z we consider and module is m, the Z m will be R m by 2, sorry 2 into Z m divided by 2 will be R m. Okay. Now, like the helical gear, this bevel gear is also having the formative number of teeth, that I already have described it. This is given by Z dash by Z cos gamma. How it has come? If we consider this surface, this circle, definitely the radius is the more from this point to this point, which is L tan gamma, and then in that circle if we consider the equivalent number of teeth of straight spar gear of the same module, that number will be more, which can be derived by Z dash is equal to Z by cos gamma. And when we consider the Lewis form factor or any other design issues with respect to the equivalent number of teeth of spar gear, straight tooth spar gear, we will consider this formative number of teeth. Now, in this slides what I have shown, that there is a gearbox, we have considered a gearbox. In this, if we look into the top open view, in this case what we find here, as if there are two sets of gear, bevel gear. This is just to manufacturer they draw in this form. This first one is a pair of bevel pinion and bevel gear of 1 ratio, and this and so this is one pair with 1 ratio, and these two is other pair with other ratio. It is shown that in the same gearbox we can put these two sets of gear. Now, next stage, so this is the input shaft and this is the intermediate shaft, and then intermediate shaft other set of gears are helical or straight part. In case of helical gears are shown. Now, view will be something like this. This is the housing for this input pinion, and here is the bevel gear. Bevel gear is not exactly straight spar gear, and it is some sort of spiral gear or like helical bevel you can say. And then what we find that this is having the helical gear, okay, helical gear set. So, the basic purpose is that of using bevel gear, that we are transmitting the power not parallelly, we are at an angle. The shafts may be intersecting and shaft may be non intersecting and offset might be there. In that case, we have to use the hypoid gears only. Okay. So, I have given the idea that what is the different type of gears and etcetera, but in this lecture or in this course we shall consider only straight bevel gear and design of that gears, and they again that is for 90-degree shafts. Now, in this case this module we have written as M bevel, that is the, because the if we consider the whole teeth of the bevel, then in that case it is inside it is of small teeth and outside it is a bigger teeth. And if we would like to compare with a standard one, we will find that if inner is matching with the standard one, outer may not match, because this is with the edge, that is gradually the tooth shape has increased. We have in this design we have considered at the middle section that will be standard. That means, if we take the section through that vertical section, we will get the standard straight spar gear. Okay. Now, that module we have considered M bevel, which is given by the formula twice T divided by S 0 is the allowable strength into the Cp is the velocity factor divided by Cw, and we can also sometimes the whole can be defined as S d. That means, that is the allowable strength we have considered designing this gearbox or designing this bevel gear, considering the necessary velocity factor, necessary wear factor, etcetera. And Z is the actual number of teeth, Y is the modified form factor, Lewis form factor, which is against the formative number of teeth. That means, actual number of teeth divided by cos of the cone angle, cos of cone angle of that respective gear or pinion. And then the psi is the width factor. If we multiply psi with m, we will get the actual width b. T is the torque we have considered for the design. It is maybe the nominal torque or maybe some with some multiplied factor depending on the dynamic condition of the load. Now, psi 0 is another factor to relate the cone length. T is the torque, Z is the number of teeth. Now, Cv is 1 for precision gears, no shock, 1.2 for general purpose gears. So, for bevel gear we can simplify that 1 or 1.2. Cw is the wear load and lubrication factor, which we can take 1 for forced lubrication, 1.5 for sump and splash lubrications. Here it can be mentioned that in comparison to helical or straight spar gear, bevel gear needs more care for lubrication because of their taper teeth, and as the shafts are intersecting, sometimes the contact is very poor. Usually bevel gear checked for contact after manufacturing. after putting into the actual gearbox, using the die the contacts are tested. If the contact is not proper, then tooth is some correction is given on the teeth, so that they come in contacts. Anyway, for that, if the lubrication, say for example, for the same condition of lubrications where we can consider 1.25 for helical gear, we should consider 1.5 for sump and splash lubrications. SD is allowable design strength in pascals, that SD already I have shown. So, which can be given yield strength by, in this case I would say this is not SD, we would put here better, that is 0, which is taken yield strength divided by 2.5 or 3. Whereas SD, as I told, that whole part can be considered as a SD. Now, we are continuing with the designs methods. Now, the psi is width factor, active width B divided by the module, whereas psi 0 is taken as B by L. B is the width, L is the cone angle, and initial design as psi also we have to assume something. So, B by L is assumed 1 by 3. Later, after the first calculation of the module, first estimation of the module, what we can do? We can find out then cone angle, etc., cone length, and then again we can calculate B by L, that is psi 0 value, and we can recheck whether module is satisfactory or not. If necessary, that value can be increased or decreased a little bit. Then the Y is same formula is used as in case of straight spar gear, and considering the formative number of teeth Z dash, which is given here. Now, mean PCD is RM or DM, you can say, that is given by Z into module of Bevel. We have considered in this way. In some design, it is outside pitch circle radius is considered. In this case, we have considered the mean radius, and gamma p is the cone angle for pinion, and gamma g is equal to cone angle of the gear, and we have considered in this design gamma p plus gamma g is equal to 90 degree, and if the teeth number are same, then gamma p is equal to gamma g, but that is very rare, which is called metering gear. Gamma is pitch cone angle, and we should remember that this relation, actually if I consider this radius, and other side this is the radius, say the ratio of this must be equal to, in terms of this is the common. So, there will come tan gamma p and tan gamma g, which is Z p by Z g. So, with these relations we can further proceed into design. Now, so wear load capacity of straight bevel gear. So, we have already given, I have shown the formula for estimating the module. This is, in this case only there is another psi 0 factor is coming. So, if we consider, we can assume that what might be the value of that, then we can arrive into design. We should keep in mind that B here, this psi factor is not as high as in case of helical gear. Usually the psi factor is kept very close to 10. That means, width is equal to module, that M module into 10 or plus minus 1 or 2, something like that, it is kept like that, and L, B by L is taken 1 by 3 for initial design, and later in finalizing we can of course vary a little bit those things. Now, the wear load capacity of the bevel gear tooth, that means at the contact surface, can be derived as DMP, that is mean diameter of the pinion bevel gear, divided by cos gamma p into B, the width which you have taken, K is the same, that factor, wear load factor, and QG, which also can be written DMG, that is diameter of the gears, divided by cos gamma g, B into K, in that case QP. Just look into this. If here in the first case, if you use the diameter of the pinion, then relation will be QG, and if you use the diameter of the gear, then that will be QP. And this QG and QP, QG is written 2 into number of teeth of gears, formative number of teeth of gears, divided by formative number of teeth of gear plus formative number of teeth of pinion. In case of QP, the numerator, in numerator Z dash G will be replaced by Z dash P. So, this calculation of QP is not a problem, and K is same as defined in case of spar gear against gear and pinion teeth hardness. So, when we are considering this hardness for the helical and straight spar gear, in the same way we can consider for the bevel gear also. Only thing we have to consider the actual the pressure angle, standard pressure angle we have taken. This means that first we calculate wear load, and for the dynamic load we consider the normal load acting at that contact point multiplied by some factor, velocity factor we consider, multiplied or divided by velocity factor, depending on how we are using this velocity factor. Then we are considering that Fw is must be greater than equal to 1.15 Fd. This means again I repeat that whatever the wear load capacity at the contact point, dynamic load should be less than that. It is usually 1.15 times less than that. So, the life will be infinity, that means there will not be easily pitting or wear. If the dynamic load is more, the first possibility is that there will be pitting, there will be material removal at the contact points. If not, there is the tooth breakage. So, for bevel gear design, the care is taken same as we are designing straight tooth spar gear or helical gear. Only difference is that the formula is slightly different, but that too is not difficult. We have to assess B and L at the first level, and we need to go for the second level calculations, because we need to modify this cone radius L, capital L, and pitch cone radius as well as also the B, the width. Now, if we consider the load on the gear teeth, as we find we have taken the load at the midpoint, we know the radius there, which is z bevel into m by 2, and torque divided by 2 will give the tangential load F t. One F t is calculated, then F n can be taken as F t into sec of alpha. Alpha is the standard pressure angle. So, F n is acting like this from this corner to the opposite corner at the tooth point, and F r straightway from these geometric relations, it can be taken as F t into tan alpha into cos gamma. Cos gamma, gamma is the cone pitch angle. We are calculating on these gears, okay? And this axial load F t tan alpha into sin gamma, okay? This is the axial load which is acting along the axis. And interestingly, in case of 90° shaft straight bevel gears, what is the tangential load acting on the pinion? That will be also acting the same load acting on the pinion. Of course, it will be in the opposite directions. We have shown only the magnitude, not the directions here. And axial load of on gear is nothing but the radial load in the pinion, because suppose this is the gear, then pinion must be somewhere here. Okay. So, whatever the axial load is there, that will become the radial load on the pinion, and what is the radial load on this gear, that will be the radial axial load on the pinion. So, that is to be remembered, and if we calculate considering any one of that, other can be easily calculated. And these all these loads depending on the point of acting, that is the midpoint, that is directly going on the shaft, and usually bevel gears, particularly bevel pinion, will be a cantilever one. So, considering the shaft loads from this configuration, from these load calculations, we can now calculate the what are the load coming on the bearing, and as well as we can also find that what will be the shaft bending moment of the shaft calculation, everything can be done. And usually bearing spacing there, you can say that in case of pinion, that is one thumb rule is 3 times the diameter, larger diameter of on which we have put one bearing. So, in this lecture we have learned about the design of bevel gear, and we have only basic idea how to estimate the module of the straight bevel gear and how the loads are acting on that, and from which we can find out the loads on the shaft. And in this series of lectures, there is not scope of detailed designing the bevel gears. However, we will solve some problem on bevel gears just to learn that what might be the modules for a same amount of load for which we go for helical gears, and maybe we will learn about a little more detail about the helical gears, and from there we will have an idea how to design a bevel gear unit also. Thank you.